to welcome you. Thanks.
Did we just lost Erwan?
I think so.
Okay. He should be back very soon, I think.
Always we have problems. Yesterday we have this meeting and today we have this meeting face to face, and we face some different problems that are always very welcome. You know, face to face you can solve a lot of problems.
Yeah, it's easier than in computer.
Sorry.
Okay, we can see you now.
Okay, I was disconnected.
Yes.
So, Georges, do you want to add something before I announce today's agenda?
No, thank you very much. Once more, I would like to thank you very much for this close collaboration. And because I believe that everybody is busy, we have to start by saying that I'm also the coordinator of the other DiTECT projects, and we will continue to have a great collaboration together. Thank you very much.
Okay. So on the program of this third webinar, we have planned 2 lectures. So the first lecture will be given by Dr. Diana Kemmer, Head of Department Product Safety and Analytics at the Fraunhofer Institute for Process Engineering and Packaging, IVV in Germany, and who is a partner of the SAFFI project. So Diana will give us a 20-minute presentation entitled Migration from Food Contact Material. So the second lecture will be given by Dr. Fadi Mohareb, reader and head of the bioinformatics group in agri-food at Cranfield University in the UK, and who is partner of the DiTECT project. So Fadi will give us a 20-minute presentation entitled the SOFRML, a data science approach to food quality and safety. So in terms of organization, I suggest that we change the 2 20-minute interventions until 11:45, and that you write your questions to the speaker in the chat. So we will invite you to ask your questions during a dedicated session of 15 minutes after the 2 presentations, knowing that the webinar must end at noon. So Diana, the floor is yours.
Yes, thank you very much, Erwan. I will try to share my screen now. And I welcome your feedback if you can see my presentation.
Yes.
Okay, very good. Okay, that worked. Perfect start. Thanks again, Erwan, for the kind introduction and the possibility to talk here to you today about food contact materials and how they are being tested and assessed. And I would like to start off with a short overview about the topics of this talk. So I will start with a definition of food contact and materials and articles, and what basic principles apply to them according to EU legislation. We will have a short glance at the migration process, and of course, how migration is being tested, and also on what analytical challenges we are approaching here, or which we encounter here. So if food contact materials make it into the headlines, they rarely make it, but if they make it, it is usually associated with some kind of crisis. For example, the case where scientists have found the photoinitiator ITX in fruit juices. You may also think about baby bottles and the question of bisphenol A, which is a kind of unsolved issue also on a global scale for years now. And the public perception is that these food contact materials are a possible threat to the consumer's health. And now let's look at what the situation about food contact material is. I would like to start off with a short definition, the legal definition, which can be found in the European Framework Regulation 1935 from 2004, which is actually on materials and articles in contact with food. And here you can find the definition that all materials and articles that are either intended to be brought in contact with food or that can reasonably be expected to be brought in contact with food shall be defined as food contact materials. And to these materials and articles, this framework regulation applies. So thinking about in detail, what are those materials and articles, you can think of any kind of food processing equipment, articles that you need for food preparation or food serving. And a large and important part are also food packaging materials, which you can see a little diverse selection in that picture. Thinking about materials, you can, or this regulation covers everything from plastics, metals, paper and board, rubber, silicones, whatever material you can think of that may contact the food. With respect to articles, most dominantly are films and bottles, also closures to bottles and sealing compounds. But if you think about food production, you would also think maybe about conveyor belts in a production site, and also the kitchenware that you use at home. In this framework regulation that I just mentioned, you will find in Article 3 the absolute basic requirements for those materials. And here it's being said that materials and articles may not transfer their constituents to food in quantities which could either endanger human health. Of course, we do not want to have poisonous or dangerous substances in the food. The second demand is that these transferred quantities shall not bring an unacceptable change in the composition of the food. So the food shall not be significantly be altered. And the third demand is that these transferred quantities shall not change the organoleptic characteristics of the food. So the smell and the taste of the food shall also not be changed. So from this definition, you can already conclude that these food contact materials are not chemically fully inert. There is an interaction between those food contact material and the filling good. And this interaction, from these different interactions which occur, we are mainly interested in the mass transfer from the packaging material into the filling food, which is shown in this picture. Here we have a polymer as a food contact material and the contacting food. And we are interested in this transfer of components which are caused by a concentration gradient in this packaging food system. So these processes, this mass transfer, can also be calculated and predicted because this migration and diffusion process can be described mathematically according to the second Fick's law, if you have all those parameters and constants known. So that's the second option to the analytical approach by analytical measurements. If we look at those migration processes, there are several factors which influence migration, or which migration depends on. And most importantly, it's the concentration of the migrating substance in the packaging material, but also the physicochemical properties of the migrating substance are important, which is predominantly the molecular weight or the molecular volume of the substance. It's also important what kind of packaging material or what kind of polymer you have, for example, because these have different diffusion properties which influence the migration process about the diffusion coefficient. And of course, the contacting food, the nature of the contacting food is also very important. For example, if you have a lipophilic substance which is migrating from the packaging material into the food, you will of course find higher levels in a fatty food than compared to an aqueous media. So here the partitioning coefficients between those different layers or the different media play an important role. And as a last point, also the time and the temperature of the food contact has an important influence. And as a thumb of rule, the higher the temperature and the longer the contact times take place, the higher the migration of a substance will be. So keep in mind, as I said in the introduction, that we want to have materials that are safe for food contact, and that these materials shall not transfer components in unacceptable quantities. This leads me to the basic question that we have if we want to assess packaging materials. Which is that how can I quickly, reliably, and also at a favorable cost determine the concentration of this specific compound or compounds in the food? So this is this fundamental question. So this question is actually addressed in the so-called compliance or migration testing, which is a quantitative determination of the transfer of components. And as I pointed out already, you have your product, your food contact article, which has to comply with the appropriate regulatory regulations in order to protect the health of the consumers. Let's have a look at what kind of substances may migrate from food contact materials or articles into food. And here we can distinguish two different categories, I would like to call it. First, there are the so-called intentionally added substances, the so-called IRs. So if you think about plastics, there you will expect the monomers or other starting substances. Typically, polymer additives are included in these materials, like stabilizer or antioxidants. Typically, you have substances from the catalyst system, and for these substances, you know their identity quite well because you intentionally use them to make the food contact material. So here you can test the migration of these substances in a very specific way. Alternatively, you can quantify those substances in the polymer itself. You have the option of mathematical migration modeling. And typically you have on either European level or on the level of the member states some kind of positive lists with those substances or with substances which are subjected to specific migration limits, for example. So you can check on compliance for these limits. Let's stick for a moment to these IRs before I come back to talk a little bit about those NIRs, which are mentioned here below. Sorry, got to go back, sorry. So typically, you start off with your sampling the food contact materials. For these migration tests, you use material which has not yet been in contact with food. You set up your migration test, and the aim here is that you simulate the real-life contact for the food contact material with the food. In the next step, you do the instrumental analysis in the lab. And next, you will have some kind of result, for example, from a GC measurement, which you have to interpret and use that for your legal compliance assessment. So talking a little bit more about those migration testing and on the compliance assessment. So you will check on regulatory restrictions which may be in place. And the best example here is for plastic materials, where we have a really well-defined regulatory setup, which is given in the EU Plastics Regulation 10/2011. So this regulation includes a very large positive list for authorized monomers and additives, and gives quite a number of limits for substances which are here authorized for the use in plastics. So this may be either specific migration limits or limits for residual contents in the materials. And here you will also find the overall migration limit as a factor to assess the inertness of the materials. Thinking about the testing scheme, you have analytical and technical descriptions in various European standards, for example, for overall migration testing, but also for how to set up specific migration tests. And of course, the vast amount probably is published methods or in-house methods, which are set up in the different laboratories. I already mentioned that the aim of this migration test is to simulate the interaction of the food with the packaging material during storage, also during the packaging process, and maybe also if you treat the food in the packaging at home. Let's say you have a packaging which may go into microwave heating, or the food may be heated in the microwave. You would also try to include these contact conditions in the migration test. And this test shall be slightly overestimative, but not too exaggerate the conditions in the test. As analysts, you know that food is quite a complex matrix. You have the fat, you have sugars, you may have proteins. All of these can make your analytical life quite difficult. And so typically in these migration tests, we do not measure in the food itself. Sorry. Okay, I come back. So typically we do not measure in the food itself, but in food simulants, which are solvents, either 3% acetic acid, some ethanol, water mixtures, or olive oil and Tenax. And the aim here is that these simulants correlate to different food types. And you can, for example, you can find that in the plastics regulation, what food types would correlate to what simulants. And secondly, you will have to translate the real-life application on contact conditions to these kind of accelerated test conditions. Typically, you don't want to wait until the shelf life of a product, which may be months or even years, but you want to gain that information, those compliance information, migration testing information in a shorter period of time. And here again, there is a correlation how to correlate the real life conditions to test conditions with regard to time and temperature. So this is just copied from the plastics regulation, where you can see how these food categories are assigned to food simulants. But it's important to keep in mind as a basic rule that the specific migration testing in food shall prevail over those results in the food simulant. So that is really a basic rule. I would like to show you one short example where the different possible or envisaged simulants are compared to a real food, which is whipping cream in this case, where the migration of diphenyl phthalate, a plasticizer, was analyzed. It was spiked into an HDPE film. And as you can see, the real food is the whipped cream. It's the green line here in the middle. And you can easily conclude from these results that the testing with water or with 10% ethanol would not really reflect the situation in the real food. And in contrast to that, you can see 50% ethanol or 95% ethanol would be better simulants, which are slightly overestimative to the situation in the real food. Let's go back to this slide you've just seen, because I would like to talk a little bit about this other category of migrating substances, which is called NIAS, non-intentionally added substances. As the name says, they are not intentionally added in the food contact materials, but nevertheless, they can be present and also they are potential migrants. So these NIAS are typically degradation products, either of polymers or additives. They can also be impurities or byproducts, for example, from the polymerization process, or they can be contaminants. And the challenge here is, of course, since they are not intentionally added, to identify their structure and to bring them to a risk assessment. So this brings me to the point where really a lot of instrumental analytics is being done. And there are different analytical approaches to identify and to characterize these NIAS. So if you have already an idea about what your NIAS substance could be, or you even know the identity, then you're on the easy side. You can develop or apply a target analysis or maybe a multi-target analysis. If you have to go for a non-targeted analysis, a screening approach, that's of course the more challenging part. I don't want to go into much detail of this scheme, but typically you would have to combine different analytical techniques depending on the nature of the potential migrants. So they may be either very volatile, where you would use some headspace GC techniques, some semi-volatiles, which are accessible by GC techniques, or you have compounds which have a more non-volatile character, which typically would be analyzed by LC techniques. I would like to show you two short examples for these NIAS. And here we have listed some side products or degradation products typically found in polyolefins. So if you make an extract and analyze it, you will typically see linear and branched hydrocarbons, some kind of polymeric structures. Typically, you would also see oxidation products. They are formed during the extrusion process of films, for example, because this is some kind of thermal stressing of the material. And these substances typically are alcohols, aldehydes, ketones, or organic acids. And you can please keep in mind that these substances often have a very low odor and taste threshold and may cause an off flavor in the food, which is, let's say, a contradiction to the demand that these food contact materials shall not alter the organoleptics characteristics of the food. A second very basic example is the degradation of antioxidants used in polymer materials. So this is an example from a PP material which was irradiated. And in comparison to the non-radiated material, you can see that the typical antioxidant or stabilizer, IRCA-FOS 168, is being degraded to some smaller molecules, which then show up in the chromatogram of the irradiated material. And this kind of degradation of antioxidants or stabilizers leads to substances which are non-intentionally added, smaller breakdown products. But for these, we are in the good situation that these breakdown products are in the meantime well described and well known among the labs, and we're also subject to a risk assessment in the meantime. So the general challenges are that we do not have harmonized or standardized methods for the identification and the quantification and the assessment of the NIAS. In some cases, not even all the IRs are known. And for a classical toxicological assessment, you would actually need a clear identification of your substance. At the same time, there is this regulatory requirement and demand that you also do a risk assessment of those non-identified or non-identified substances or substances where you only have a vague idea what their identity or chemical structure could be. There are guideline documents around which typically propose a tiered approach for these assessments, depending on the migrating quantities. And there are also, it is also proposed to use combinations with new techniques like bioassays, which were introduced, I think, in the last joint webinar by Bart van den Berg. So maybe you can go back to that talk if you're more interested in those bioassay approach. So this brings me to my summary about the food contact materials. These materials are usually quite complex mixtures of known intentionally added substances, but also of unintentionally added substances, which both can migrate into the food. The basic safety requirements of Article 3 of the Framework Regulation must be respected. And this is really a challenge if you have no or little information about these NIAS components. From an analytical point of view, there is no single analytical method to detect all those possible migratable NIAS, and you would have to use some different screening approaches for different groups of substances. And it is really essential to use a combination of these screening approaches to yield the maximum amount of information. And yeah, again, as a rule of thumb, the more you know about your IAS, the better is the chance for the identification of the NIAS. So I thank you for your attention, and I'm looking forward to your questions after the second talk.
Thank you, Diana, for this excellent and extremely didactic presentation. So I suggest that, as planned, we continue directly with Dr. Fadi Mohareb's presentation and keep the questions you would like to ask Diana for the question session at the end of Fadi's presentation. So again, Dr. Fadi Mohareb is reader and head of the bioinformatics group in agri-food at Cranfield University in the United Kingdom, and is partner of the DiTECT project. And Fadi will give us a 20-minute presentation entitled the SOFRML, Data Science Approach to Food Quality and Safety. So Fadi, the floor is yours.
Thank you very much, everyone, and very interesting presentation from Diana. I'm gonna refer to some of the points that she mentioned also in my presentation. Okay. First challenge, let's share my screen. I hope that you can see the screen. Interrupt me if you cannot.
Yes, perfect.
Yes, so I'm gonna be talking about SORFML, which is an online platform that we developed some years ago, and it also has been involved or is going to be involved in the DiTECT project. I took the brave decision to switch between a presentation and a live demo. So I do hope that that is going to work. My presentation is actually quite a long one, but I'm going to take some snapshots only to talk about 5 or 10 minutes maximum on the actual talk, because I would like to give you guys some live demo about SORFML. I'm interested in your questions as well. So generally speaking, what I'm going to be talking about is the current trends of in food quality and safety, and the solution from the future of food science, at least from our point of view, and then move directly to SORFML. So in terms of the current trends, basically, we have 3 main problems that we're dealing with. The first one is safety, as we've seen in the previous talk, from the chemical contaminants, but sometimes it's biological, environmental contaminants. Food should be safe to eat. The quality of the food, it should be acceptable to the consumer, and authenticity. If we buy extra virgin olive oil, it should be extra virgin olive oil. It should not be a car oil. That's at least how a bioinformatician would see it. So in terms of safety, generally speaking, food should be safe to eat, should not include any thing that will cause harm to the human health. I'm going to particularly focus on biological pathogens, so things like Salmonella or E. coli. But generally speaking, or from a mathematical point of view, as a bioinformatician, although this is a much more serious problem, mathematically, it's a simple problem because it's a binary problem. It's you only need to have 1 E. coli in your sample to call it contaminated, 1 Salmonella to call it contaminated. So it's a binary, it's a yes or no question. As opposed, for example, to the food quality, which is a very large gray area, from the food being fresh and acceptable to the consumer up to the point where the food is unacceptable. The consumer does not buy it from the market or the supermarket, and basically it goes to waste. And now there is, of course, quite a lot of buzz around the carbon footprint of food and how much impact it has on the environment. And if we talk about 1/3 of the food being wasted globally and within the EU, there is definitely quite a lot of room for improvement that should be done on food on that aspect. And the third problem, as we hear from the food scientists, is basically the authentication, making sure that the whatever is described on the food label is basically what the consumer is going to buy. Currently, the 100% inspection of the food, either is in relation to quality, safety, or authentication, is technically and financially impossible. So when we talk about food quality, for example, basically what happens is that the food manufacturer or the factory will send a sample to the lab. They will do the conventional microbiological tests, and 2 or 3 days later, the results will come back. So obviously it's very time consuming. It requires lots of the deployment of lots of analytical platforms, lots of bacterial media, and all this kind of things. And also it gives a retrospective answer. So that means by the time the lab send the results back, the product might have already left, might be already in the consumer fridge. So because of that problem here, the manufacturing box that we see here is basically sending regular samples to the either the internal or external food laboratory, but the product will continue to go on through the food manufacturing distribution chain and will reach the consumer. Sometimes it reach the consumer before the results come back. And that would result in product callbacks. So seen from Diana's talk that she started with when food make headlines in the news, it's usually not a very good thing. And I completely agree with that. So I included some examples here from the horse meat scandal that happened in the UK a few years back. And if you register to EFSA or the Food Standard Agency here in the UK, then you get lots of news alert about food being called back. And of course, that's very, very damaging to the business, and it's damaging to the consumer trust in the food products that they are buying. So we heard during Easter time about the problem with the Kinder Surprise eggs. As someone who has a 5 years old, that was a big deal that we're not getting Kinder Surprise for Easter, and of course, it's very damaging to the business itself. That's another example from salmonella contaminated eggs by Aldi a couple of years ago. So what we're trying to do in general and specifically in DiTECT is basically to deploy some of the rapid non-invasive techniques, analytical platforms that can be applied online or at line throughout the food production chain. And hopefully that will give a real-time assessment of the food product. And in order to achieve that, as I said, the technique itself need to be rapid, need to be non-destructive, something that ideally you would implement during the process, the manufacturing or the packaging. The data from that analytical platform would go into a cloud system or an online platform, and it will be assessed against a mathematical model that will take something like a hyperspectral imaging or a multispectral image of the food, and from the wavelength, it can then translate that into safe, unsafe, or fresh, unfresh type of answer. And ideally, that whole process should not take more than a couple of minutes, because you are ultimately seeking real-time monitoring. So when it comes to the analytical platforms, we are focused on things that are generally portable, so they can be applied online or at line. It should be fast. It should be ideally non-destructive. So one of our partners, Mike Carsten, he presented during the last workshop, the guy behind Videometer. It's basically a multispectral imaging camera that takes an image snapshot of the product. We then take that raw image, translate it into different channels, and then expose that to a trained machine learning model that can translate that image into either a classification problem, safe, unsafe, or a regression. So you can predict the bacterial count, for example, from taking an image snapshot of the meat product in that example. So that's basically what we would like to do. So within SORFML, the machine learning challenge that we have is that those kind of rapid techniques usually give you a multiple column matrix. So depending on the technique, if it's an FTIR, every column will be different wavelength. If it's an electronic nose, you will have 14 or 16 sensors, each one for a particular volatile oil, volatile compound. For Videometer as a multispectral imaging technique, it will give you 18 wavelengths. So we need to translate that into a raw table, ideally in a CSV format. And then from that table, we can start building classification or regression models that can give an answer back to the device, if it's a connected device, or back to person running the device. I'm not going to go through different machine learning algorithm. We can simply skip that. So generally speaking, for machine learning, what you're trying to do is to unravel or identify hidden patterns within your data. So in that example, I've got different shapes, triangles and circles. Triangles are green, circles are in blue. And what I try to do is basically to train a model to give me an answer, either to separate those objects by color or to separate them by shape. And I can fine tune the model up until I reach an accuracy, an acceptable accuracy. So something within between 70 and 90% accuracy, correct answers. And once I'm happy with that model, it can be then deployed and work in tandem with the analytical platform. So generally speaking, if I have a sample of beef, for example, what we do is that, or not me myself, but the George Nicha's group, for example, for the microbiology lab, they will store the sample under different storage temperature, different time point, basically to have different scenarios that we can train our mathematical model with. And for each sample, they will go through the microbial analysis itself, because that's basically the labels of my samples, the output that I would like the model to predict. I train the model on the different temperature, on different storage condition, and I assess the performance. Can my model predict the bacterial count? It can be a total valuable count, or it could be a particular bacterial count if I'm interested specifically in Pseudomonas, for example, lactic acid bacteria. And that's the part that we do within my group. So basically, you would have a matrix where you have different samples as rows, and the columns will stand or will depend on the analytical platform that you take. Could be from few columns. If you're dealing with a technique like electronic nose, you will have 14 columns, or it can be several hundred columns in the case of FTIR, for example. You divide your data into training and testing. You use the training data to build the model, to optimize the statistical parameter, and then you keep some of the data on the side, not exposed to the model. And basically, that's what you use to assess or to validate the prediction accuracy of your model. That's in very general terms. So what we try to do then with SORFML is basically to allow a food scientist, not necessarily having the computational or the statistical expertise to build this machine learning models themselves, to try different scenarios. So we built a platform called SORFML. You can access it by sorfml.com. It's a web platform, and basically what you do is that you can sign up with a username, and you can browse in the existing experiments stored on the system. You can add your own experiment as well. And basically what you can do is to build on the web platform some machine learning methods or some machine learning models using different algorithms. And the idea here is basically a typical user will ask themselves the question, okay, I have this sample, this yogurt sample, for example. I'm interested in lactic acid bacteria. I would like a model that can predict lactic acid bacteria, but I don't know which machine learning method should I use, or which analytical platform would perform best. Is it FTIR? Is it electronic nose? Is it GCMS? So they will try, they will run all the experiments using all these devices, and then they upload the data on SORFML and do a kind of a grid search, try all the machine learning algorithms implemented within the system versus all the analytical platforms that they have. And at the end, they will get a report telling them, okay, if you want to predict, for example, lactic acid bacteria, the best platform to use could be FTIR. And what you need to do is to apply random forest in tandem with FTIR. That's the typical scenario that we're dealing with. So I'm going to go to SORFML now. So this is how the platform looks like. and you can go to the home page. You can create your own experiment here. So you basically add the experiment name. Let's say it's a meat spoilage experiment. You add the data. You can choose the visibility of your data, so you can make your data public for other researchers to use, or you can make it private, or you can share it with a particular user on the system. So I can share that experiment, for example, specifically with George in that case. So only George can see it on his workspace. Then you press next and you upload your experiment files. So here in these files, I have done an experiment using eNose, FTIR, GCMS, HPLC. I can upload one at a time, or I can upload all of them. You select the type, select eNose, and then you can keep adding as many data sets as you want. Once you're done, your data will appear on the system. So let's go to the already added experiments here. I hope you can see my screen. So this is an experiment on meat spoilage stored under aerobic conditions. So in that example, I have several analytical platforms. So each one of these samples was analyzed with electronic nose, FTIR, GCMS, HPLC, and videometer. Basically, what you can do is you can search or download or share the data with other users, or you can perform some initial statistical analysis of your data. So you can do principal component analysis, see, okay, how likely would I get a very accurate model if I use videometer, for example. So you can go here, can perform a PCA plot on the fly, and you can color your samples based on the bacterial count for each one of these samples. So here I'm displaying the sample names, for example, and I can color them by total viable count. And you can see here that, okay, that is more likely to give me a good classification because there is a kind of separation. You can draw a sigmoid curve here between the spoiled samples as colored by the bacterial count, so the reddish or the orange sample, versus the green ones, which are the fresh samples. Or you can build a mathematical model itself. So let's say I would like to build a regression model to predict bacterial count. So I can choose a new model from here. I can choose which analytical platform I want to build the model on. So let's say I choose Videometer and Electronic Nose, and I would like to predict 2 of my bacterial spoilage. And these are the machine learning methods that I can apply. So let's choose something that doesn't run forever, k-nearest neighbor, for example, and random forest. You click next. You can choose the statistical parameters of the data, whether you would like to perform any pre-treatment, any scaling of the data. You click on next, and then you choose the statistical parameter for k-nearest neighbor and random forest. Once you click end, basically what is happening now on the background is that the server itself will perform a grid search to build some models for you based on the selection that you've done, and it will display for you the output of that model. So you can either choose the model and gain more details about that particular mathematical model, or you can see a PDF report. If I can open that from here. So you can get a report that looks like that, that will tell you, okay, straight away, the best performance for predicting total viable count was using Videometer combined with k-nearest neighbor. And if you scroll through, it will give you more details about that model and how it is built. So finally, basically to conclude, what we're trying to do here is within SORFML, we try to combine different assessment of different pilots. We have 3 pilots within the DiTECT project based on beef, fish, chicken, and corn. And we have a central data repository that will collect all the experimental data that our research partners are conducted. And we are going to build a system that will allow real-time monitoring of the product. So now we managed to tackle the sensory problem. We have sensors that can give good prediction accuracy, because that's what we've been testing over the years. We have an online platform that can accept the output from these sensors and can build a machine learning model. The user can store the model on the system, and the next step will be basically by scanning the product will be assessed by scanning it using Videometer, for example. That image will go on the cloud, will be assessed via the machine learning model that is already stored on the system, and will give back the user an answer about how the freshness profile or the predicted bacterial count of that product would look like. So we'll allow real-time monitoring, and because these sensors are portable and rapid and are non-destructive, they can be implemented through different time points throughout the food manufacturing or production chain. So sorry if it was a little bit rushed. I hope that gave you an overview of what we're trying to do here in SAFFI. Thank you very much for the invitation. I'm happy to take questions.
Thank you very much, Fadi, for this extremely lively and stimulating presentations, which gives a very good illustration of what bioinformatics and more particularly machine learning can bring to the field of food safety.
It's very good when the demo works. When the demo doesn't work, it's a complete disaster. Today was a lucky day.
So we now have a bit less than 7 minutes for the participants to ask their questions to the speakers. I've seen that we have a question from Joe Tierney. So maybe Joe, you can ask directly your question to Diana, I believe.
Yes, yeah, hello all. Diana, very good talk. I just had a specific question on, I suppose there's 2 pieces to it really, on the analytical equivalence. So I suppose let's say in the US there's the ASTM, and then there's obviously the 1935 linked analytical methods, and then China would have their own for migration testing. Within that, I suppose, when we look for declarations of conformity on materials, what's the from an underlying equivalence perspective, what would be your analytical view on how equivalent they would be between the different regions?
Thinking about the pieces of legislation, they are really different worlds, actually. So there's no automatic vice versa compliance. So you're compliant with EU legislation. It's not necessarily that you comply with US legislation. If you think how migration testing shall be done, for example, if you want to bring a new substance to the respective positive lists or do a food contact notification in the US, it is pretty easy to design the experiments that they work for all these 3 areas. In particular, the Chinese have set up their modernized their legislation and their demands in the, let's say, last 5 years. And they have a pretty similar approach as the Europeans, thinking about positive lists and how migration shall be done. So there are very small differences in the migration testing scheme. And as I said, if you want to bring a substance for a food contact notification process, the demands from FDA are also not that different. But how the legislation is set up, there are differences indeed.
Super, thank you. And the other one was just related to the post-consumer recycled packaging. I know it's an emerging area and a need to use more recycled packaging. There's some, I suppose, potential increase in use of over a period of time. Has there been any thoughts given to that, Diana, around specific target residues for recycled packaging at all?
For Europe and also for the US, I can say that PET is really working. So US FDA and EFSA have evaluated the safety of, I don't know, more than 200 recycling processes specifically for PET. So this is really for over 10 years or 15 years, PET materials are brought back into the market based on closed loop approaches, and they are being reused in direct food contact. But this is due to the fact that we have closed circles here, bottle-to-bottle recycling, and that the PET as a polymer is very low, has low diffusion properties. So this makes it easy. The situation for polyolefins is different. So here, with the safety requirements which are currently set in Europe, it's not possible to show the safety of those materials to bring them currently to bring them back in direct contact. So you need some other solutions here. And of course, we are working on that issue because, we want to strengthen our as a society. We have the wish to strengthen recycling and reuse of those plastic materials.
Super. Thank you, Diana.
You're welcome.
So Diana, I had a question for you. You already mentioned about it a bit in your presentation, but what are the emerging migrants? That is to say, those for which the regulation is just beginning to take an interest in the field of food packaging, and which are likely to be hot topics in the years to come?
Yeah, I make it short because I think we're running out of time, and there's some questions for Fadi as well. It's not so much single or individual substances or groups. The focus is actually on those non-harmonized materials with a regulatory aspect, which are not harmonized on EU level, which is predominantly for packaging, paper, and board. That's of interest. The reuse of post-consumer recyclates. And maybe as another topic, it's printing inks, because they are extremely complex and have lots of migratable substances included.
Thank you for this brief answer, because yes, we are running out of time. And for Fadi, I had a question, quite general question in the particular field of real-time measurements. Processing time seems to be a major constraint for machine learning methods. So how do you manage, how do you take this criterion into account? Does it prohibit the use of certain methods? Does it require particular hardware?
No, not necessarily. It's actually a very valid question. So the bottleneck really when it comes to applying machine learning is in the process of building and optimizing the model. Okay, and this is basically when you take the experimental data. So someone like George will do 120 samples, take 120 images for them. And I need to build a model, do the grid search. That will take on the server, and it's not a very fast server. It's basically a 10,000 pounds one. It's we build it ourselves. It will take about half an hour, which is not acceptable to be applied in real time. But this is only for the process of building the model. So the decision that we took is that we run the experiments, we run the model offline. Once the model is stored on the server, so the validated model is there, it only takes a couple of seconds for an existing model to test new data against it. So when you apply it in real time, it's actually very, very fast. It's faster. The main bottleneck is not the machine learning in that case. The main bottleneck is sending the image through the network. So that's all. But the machine learning would work very fast once the model is optimized.
Okay, thanks. So I think it's time to close this webinar, unfortunately. So before closing it and wishing you a good end of the day, wherever you are, I would like to warmly thank the two speakers for their excellent, very lively and didactic presentation. And I would like to thank the members of the two consortia for their active participation in this appointment. So if George agrees, I already suggest that we meet for a fourth webinar, which, if we follow the logic applied until now, will be organized by DiTECT. So perhaps we could also get in touch with George on the sidelines of these webinars to discuss other forms we could give to our interactions. So George, what do you think?
Yeah, I totally agree with you. Already we have, there is a candidate from DiTECT that will be a Chinese Tsinghua University, Professor Tsinghua. So we have arranged the subject, and she will, I will contact you to specify the subject, but
Okay.
that this time will be microbiological subject.
Great, fantastic. So I think it is now time to close the session.
Yep.
So once again, I would like to thank you all for your participation, and I wish you an excellent end of the day or beginning of the evening for the Chinese colleagues. Bye-bye.
Bye-bye. Thanks a lot.
Thank you. Bye-bye.
Bye.
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 Great talk.
Okay.